Hey students, this is your Nandini ma'am. Today we are going to read chapter number 1 of ICSE Chemistry Class 10th, and the chapter is Periodic Table, Periodic Properties and Variations of Properties. Introduction. Elements are pure substances made up of one type of atoms. They are the basic units of all types of matter. In order to study elements in an organized manner, they need to be classified. You have studied in class 9th contribution of Daubonnier, Newland and Mendeleev to the classification of elements. Daubonnier grouped the elements in three of triads. Newland observed that when elements are arranged in increasing order of their atomic mass, every eighth element, beginning from any element, resembles the first element in its physical and chemical properties. Dmitry Mendeleev, a Russian chemist, gave the first periodic table of elements based on his law, which states that the properties of elements are the periodic functions of their atomic masses. This arrangement enabled Mendeleev to place 63 elements known at that time in vertical columns, groups, and in horizontal rows, periods. He predicted the existence of those elements which were yet to be discovered. But this method could not explain the positions of certain elements, the rare earth metals, and the isotopes. These defects were removed when Henry Moseley put forward the modern periodic table. He stated that the physical and chemical properties of elements are the periodic functions of their atomic number. Later on, Niels Bohr gave the extended form of the table known as long form of the modern periodic table given on page 2. A tabular arrangement of elements in groups, which is vertical columns, and periods, that is horizontal rows, highlighting the regular trends in properties of elements is called a periodic table. Salient features of the modern periodic table. Groups. The modern periodic table has 18 vertical columns. They are known as groups arranged from left to right in the order. Group 1. These elements are known as alkali metals as they form strong alkalis with water. Group 2. Alkaline earth metals, they form weaker alkalis as compared to group 1 elements. Groups 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12 are known as the transition elements. They have their two outermost shells incomplete. Group 13, boron family. Boron is the first member of the group. Group 14, carbon family. Group 15, nitrogen family. Group 16, oxygen family, also known as chalcogens, meaning ore forming. Group 17, these elements form salts and so are known as halogen. Group 18, zero group, elements of this group are called the noble gases or inert gases. These elements have their outermost orbit complete. Due to stable electronic configuration, they hardly react with other elements. Note, the elements of groups 1, 2, 13, 14, 15, 16, and 17 are known as the main group elements or representative elements or normal elements. The outermost shell of all the elements of these groups are incomplete. Periods. There are 7 horizontal rows in the modern periodic table. They are known as periods. The number of shells present in an atom determines its period. For example, elements of period 1 have only one shell. Elements of period 2 have 2 shells and that of period 3 have 3 shells and so on. Note, lanthanides group 3 of the 6th period and actinides group 3 of the 7th period have similar properties because they belong to the same group 3. They are shown at the bottom of the periodic table because they are large in number and if shown in the main body of the table will distort its shape. The third period elements, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine summarize the properties of their respective groups and are called typical elements. A period is determined by the number of shells and a group is determined by the number of electrons present in the outermost shell. For example, sodium has atomic number 11 and its electronic configuration is 281. It has 3 orbits or shells and has 1 electron in the outermost orbit. Hence, it is placed in third period and group 1. Similarly, calcium, atomic number 20, electronic configuration 2882, is placed in fourth period and group 2. Periodicity. The properties that reappear at regular intervals or in which there is gradual variation, that is, increase or decrease at regular intervals, are called periodic properties, and the phenomenon is known as the periodicity of elements. Cause of periodicity. The cause of periodicity is the reoccurrence of similar electronic configuration, that is, having same number of electrons in the outermost orbit. In a particular group, electrons in the outermost orbit remain the same, that is, electronic configuration is similar. Since chemical properties of elements depend upon the number of electrons in their outermost shell, thus, elements of the same group have similar properties. For example, in group 17, that is halogens, all elements have 7 electrons in their respective outermost shells. Therefore, they show similar properties such as they are colored nonmetals, they form negative ions carrying a single charge, for example, chloride ion. They are very reactive and are therefore found in combined state. They are only slightly soluble in water, but they dissolve much better in organic solvents like carbon disulfide, chloroform, alcohol, etc. Their melting and boiling points increase regularly moving down the group. They are good oxidizing agents. It is thus concluded that periodicity is due to the same number of electrons in the outermost orbit of different elements, shells, and valency. Orbits. Electrons revolve around the nucleus in certain definite circular paths called orbits or shells. Number of shells. Down a group, that is, from top to bottom, the number of shells increases successively, that is, one by one, such that the number of shells that an element has equals the number of the period to which that element belongs. Across a period, that is, from left to right. On moving from left to right in a given period, the number of shells remains the same. For example, in the second period, the number of shells remains 2, that is, equal to the number of the period. Similarly, in the third period, the number of shells remains 3 and so on. Valency. Valency denotes the combining capacity of an atom of an element. It is equal to the number of electrons an atom can donate or accept or share. On moving down a group, the number of electrons in the outermost shell, that is, valence electron, remains the same. Therefore, valency in a group also remains the same. In a given period, the number of electrons in the valence shell increases from left to right, but the valency increases only up to group 14, where it becomes 4, and then it decreases, that is, in group 17, it becomes 1. Note, valency depends on the number of electrons in the outermost shell, that is, valence shell. If the number of electrons present in the outermost shell are 1, 2, 3, or 4, then their valency is 1, 2, 3, or 4 respectively. If the number of electrons present in the outermost shell are 5, 6, or 7, then their valency is 3, 2, 1 respectively. Valency is the combining capacity, so it is always positive. In the periodic table, elements are arranged in order of increasing atomic number. The vertical columns of elements with similar properties are called groups. The horizontal rows are called periods. Periodic properties. The properties of elements which are directly or indirectly related to their electronic configurations and show a gradual gradation as we move across a period from left to right or down the group from top to bottom are called periodic properties. Important periodic properties are atomic size, metallic character, non-metallic character, ionization potential, electron affinity, and electronegativity. Atomic size or atomic radius. It is the distance between the center of the nucleus of an atom and its outermost shell. Atomic radius can also be defined as half the internuclear distance between the combined atoms in a molecule. Unit: Armstrong. 1 Armstrong is equal to 10 to the power minus 10 meters. Picometer. 1 picometer is equal to 10 to the power minus 12 meter. Atomic size depends upon number of shells and nuclear charge. Number of shells. An increase in the number of shells increases the size of an atom because the distance between the outermost shell and the nucleus increases. Nuclear charge. It is the positive charge present in the nucleus of an atom, which is equal to the number of protons in the nucleus, that is, the atomic number. An increase in nuclear charge decreases the size of the atom because the electrons are then attracted towards the nucleus with a greater force, thereby bringing the outermost shell closer to the nucleus. Trends in atomic size. Down a group. In a group, the size of an atom increases as one proceeds from top to bottom. This is due to the successive addition of shells as one moves from one period to the next in a group. For example, elements in group 1. In group 1, the size of hydrogen is smallest and that of cesium is largest. In group 17, the size of fluorine is smallest. Across a period. In a period, the size of an atom decreases from left to right. This is because the nuclear charge, that is, the atomic number, increases from left to right in the same period, thereby bringing the outermost shell closer to the nucleus. Therefore, considering the second period given above, it has been found that lithium has the largest atomic size, while fluorine has the smallest. In the third period, sodium is largest in size. Note, as an exception, the size of the atoms of inert gases are bigger. This is because the outermost shell of inert gases is complete. They have the maximum number of electrons in their outermost orbit, thus the electronic repulsions are maximum. Hence, the size of the atom of an inert gas is bigger. Note 1. Cation is always smaller than the parent atom from which it is formed. Reason. Cation is formed by the loss of electron. Hence, protons are more than the electrons in a cation. So, electrons are strongly attracted by the nucleus and are pulled inward. Hence, the size decreases. Anion is larger than the parent atom. Reason. Anion is formed by the gain of electrons. Thus, the number of electrons are more than the number of protons. The effective positive charge in the nucleus is less, so less inward pull is experienced, hence the size expands. Size of isoelectronic ions, that is, the ions having the same number of electrons, depends upon the nuclear charge. Greater is the nuclear charge, smaller is the size. Metallic character. Those elements which have a tendency to lose their valence electrons and form a positive ion are considered as metals. Hydrogen is an element which does not have a neutron. It has only one electron and one proton. On losing this electron, it forms its cation, which has only one proton. Therefore, its cation can also be called a proton. The metallic character of elements depends on atomic size, nuclear charge. Atomic size. The greater the atomic size, the farther the outermost orbit, and thus lesser the nuclear pull exerted on it. As a result, electron can be easily removed from the valence shell, thus making the elements more metallic. Nuclear charge. The greater the nuclear charge, the greater is the force exerted by the nucleus on the electron of the outermost orbit. This makes it difficult to remove the electron from the outermost orbit. Thus, metallic character decreases. Elements which lose electrons to complete their octet are reducing agents. Metals are good reducing agents. Greater the tendency to lose electron, stronger is the reducing agent. Trends in metallic character. On moving down a group, the atomic number increases and the nuclear charge also increases. The effect of an increased atomic size is greater as compared to the increased nuclear charge. Therefore, metallic nature increases as one moves down a group. For example, in group 1, lithium is the least metallic element. Note, francium is radioactive element, so its properties are not new. Across a period. On moving across a period, nuclear pull increases due to increase in atomic number and thus the atomic size decreases. Hence, elements cannot lose electrons easily. Therefore, the metallic character or nature decreases across a period, moving from left to right. Example, in the second period, lithium is the most metallic. In the third period, sodium is the most metallic element. Non-metallic character. Those elements which have a tendency to gain electrons in order to attain octet in their outermost orbit are considered as nonmetals. Nonmetals usually have 5, 6, or 7 electrons in their outermost orbits. They can gain 3, 2, or 1 electron respectively in order to attain octet or to complete their valence shells and form an anion. For example, chlorine and oxygen gain 1 and 2 electrons respectively to form anions. Non-metallic character also depends on atomic size and nuclear charge. Atomic size. The smaller the atomic size, the greater is the nuclear pull and the tendency to gain electrons. Therefore, the element is more non-metallic by nature. Nuclear charge. The greater the nuclear charge, the greater is the tendency to gain electrons, and hence more non-metallic is the element. Trends in non-metallic character. Down a group. The atomic size increases due to the addition of new shells over successive periods. Though the nuclear charge increases due to an increase in atomic number, the effect of an increasing atomic size is greater. Therefore, non-metallic nature decreases down the group. Across the period, left to right. On moving across a period, the tendency to gain electrons increases due to an increase in nuclear pull and a decrease in the atomic size. Therefore, non-metallic character increases across a period, that is from left to right. Note, nonmetals are oxidizing agents. The nature of oxides also show periodicity. Across a period, the oxides of elements in a particular period show decreasing basic nature and finally becoming acidic. For example, oxides of the elements of the third period. Down a group, the basic nature of oxides of metals increases. Chemical reactivity. The reactivity of elements depend upon their tendency to lose or gain electrons to complete their outermost orbit. Greater the tendency to lose electron, greater is the reactivity in the case of metals. Similarly, greater the tendency to gain electron, greater is the reactivity of nonmetals. Trends in chemical reactivity across a period. On moving from left to right in a period, the chemical reactivity of elements first decreases and then increases. The group 1 element can lose electrons easily as compared to group 2. Similarly, group 2 elements can lose electrons easily but only in comparison to group 30 and not at all in comparison to group 1. As the tendency to lose electrons decreases, reactivity also decreases, and thus silicon is the least reactive element in third period. As we move from phosphorus to chlorine, the tendency to gain electrons increases and hence reactivity again increases. Down the group, the tendency of losing electrons increases down the group. Since chemical reactivity in metals depends upon the tendency to lose electrons, thus reactivity increases on going down the group. The most reactive metal is at the bottom of group 1. The chemical reactivity of nonmetals decreases on going down the group as it depends upon the tendency to gain electrons, which decreases down the group. The most reactive nonmetal is at the top of group 17, that is fluorine. Gradation in physical properties. The melting and boiling points of metals decrease on going down the group. The melting and boiling points of non-metals increase on going down the group. Across a period, left to right, melting point and boiling point usually increases up to group 14 and then decreases. Density of elements across a period increases gradually to maximum and then slightly decrease may be noticed. Down a group, density of elements increases gradually. Ionization potential or ionization energy or ionization enthalpy. We know that the electrons in an atom are attracted by the positively charged nucleus. So, if we want to remove an electron from an atom, some energy has to be supplied to overcome the strong attraction of the nucleus. And after the electron gets removed from the atom then acquires 1 unit positive charge and becomes a positive ion or cation. The energy required to remove an electron from a neutral isolated gaseous atom and convert it into a positively charged gaseous ion is called ionization potential, ionization energy, or first ionization energy. Unit. Ionization energy is measured in electron volts per unit per atom, and its SI unit is kilojoules per mole. Ionization energy depends on atomic size, nuclear charge. Atomic size. The greater the atomic size, the lesser the force of attraction. Since the electrons of the outermost shell lie further away from the nucleus, thus make their removal easier. Hence, the ionization energy required is less. Nuclear charge. Greater the nuclear charge, greater is attraction for the electrons of the outermost shell. Therefore, the electrons in the outermost shell are more firmly held, because of which greater energy is required to remove the electron. Trends in ionization energy across a period. The ionization energy tends to increase as one moves from left to right across a period, with exceptions, because the atomic size decreases due to an increase in the nuclear charge, and thus more energy is required to remove the electrons. Down a group. There is an increase in atomic number and atomic size down the group due to the addition of extra shells. This increase in the atomic size overcomes the effect of an increase in the nuclear charge. Therefore, ionization energy decreases with an increase in the atomic size, that is, it decreases as one moves down the group. Note, helium will have the highest ionization energy, 2372 kilojoules per mole, while cesium will have the lowest ionization energy of 375 kilojoule per mole. Metals usually have low ionization energy, whereas nonmetals have high ionization energy. Electron affinity or electron gain enthalpy. We have just studied that to remove an electron from an atom, energy is required. Similarly, when an extra electron is added to an atom, energy is released. The amount of energy released while converting a neutral gaseous isolated atom into a negatively charged gaseous ion, that is an ion, by the addition of electron is called electron affinity. Unit, electron volt per atom or kilojoule per mole. Electron affinity is represented by a negative sign. Electron affinity depends on atomic size and nuclear charge. Atomic size. The smaller the atomic size, the greater the electron affinity, because the effective attractive force between the nucleus and the valence electrons is greater in smaller atoms, and so the electrons are held firmly. Nuclear charge. The greater the nuclear charge, greater is the electron affinity, because increase in nuclear charge increases the effective attractive force on the valence electrons. Variations in electron affinity. In a period that is from left to right in a horizontal row of the periodic table, the atomic size decreases and the nuclear charge increases. So, the electron affinity increases. Thus, electron affinity is the highest for group 17 elements and the least for group 1. Down a group. Moving from the top to the bottom in a group, the atomic size increases more than the nuclear charge, thereby causing a net decrease in electron affinity. Note, In group 17, fluorine has lower electron affinity than chlorine, and in group 16, oxygen has lower electron affinity than sulfur. This is because the size of fluorine and the oxygen atom is very small. As a result, there are strong inter-electronic repulsions, and thus incoming electron does not feel much attraction. Electronegativity. The tendency of an atom in a molecule to attract the shared pair of electrons towards itself is called its electronegativity. Electronegativity is a dimensionless property since it is only a tendency. It only indicates the net result of the tendencies of different elements to attract the bond-forming electron pair. Electronegativity is measured on several scales. The most widely used scale of electronegativity was devised by Linus Pauling, in which the highest value of electronegativity is taken as 4.0 and the lowest as 0.7. Electronegativity values too depend on size of atom and nuclear charge. Atomic size. The greater the size of the atom, the lesser the electronegativity, since the electrons being farther away from the nucleus experience a lesser force of attraction. Nuclear charge. The greater the nuclear charge, the greater the electronegativity, because increase in nuclear charge causes electron attraction with a greater force. Trends in electronegativity across a period. Since the nuclear charge increases due to an increase in atomic number, electronegativity increases from left to right in a period. For example, in the second period, electronegativity increases from lithium to fluorine. Down a group. There is an increase in atomic number down a group, that is nuclear charge increases. But due to the addition of extra shells, the atomic size increases. The effect of an increase in the atomic size overcomes the effect of an increase in the nuclear charge. Hence, electronegativity decreases down a group. For example, in the first group, it significantly decreases from lithium downwards to francium. Note, generally metals show lower electronegativity as compared to non-metals. Thus, metals are electropositive and non-metals are electronegative. The elements of second period differs in properties from their respective groups. This is due to small size of the atom and their high electronegativity. Diagonal relationship. The elements of the second period show resemblance in properties with the elements of the next group of the third period due to very less electronegativity difference. This leads to a diagonal relationship, and these elements are called bridge elements. Noble gases have complete octets, so they do not have tendency to attract electrons. Note, greater the value of electron affinity, easier it is to gain electrons, and more non-metallic or more electronegative or more oxidizing is the element. Relation between atomic number and mass number of light elements. Atomic number, Z. The atomic number of an element is equal to the number of protons in the nucleus. Atomic number is the unique property of an element because no two elements have the same atomic number. Significance of atomic number. Atomic number is equal to number of protons is equal to number of electrons. It distinguishes an element from other elements because no two elements have the same atomic number. It gives the electronic configuration of an element. It helps us finding the position of an element in the periodic table. Mass number represented by A. The mass number of an element is the sum of the number of protons and neutrons in the nucleus of the atom of that element. A close look at the electronic configurations of lighter elements reveal that the elements which have an even number of protons, for example, atomic numbers like helium, carbon, have their mass numbers twice the atomic numbers, except beryllium and argon. Elements which have an odd number of protons have their mass numbers twice the atomic numbers plus 1. Note, elements with N by P ratio around 1 are stable. That is, light metals like sodium, potassium, calcium, and elements with N by P ratio 1.5 and above are radioactive, and that means they emit radiations. They are unstable elements, for example, heavy metals like uranium. So with this, we finish off our chapter number 1. Do study well and listen to the video and mention your doubts in the comment section. Thank you so much.